Welcome back, guys. We're here doing our third part of the second reactions lecture. Again, we're doing more introductory stuff. A lot of the stuff you'll see throughout this course. So stay focused, I guess. I don't know. You don't have to. If you don't want to, you can just leave this and go play video games or something, or read your book. Okay. So, fractional conversion. It is defined as the current extent of reaction over the hypothetical max extent of reaction. The reason this is important is because it tells you how much of something has already reacted. That's the important part. Now, it sounds similar to the extent of reaction, but the only difference is that fractional conversion is compared to the theoretical maximum extent of reaction. Now, this is also defined as the moles of limiting reagent at a current time is equal to the initial moles of a limiting reagent 1 minus the fractional conversion. Right? This is also defined this way. Now what this means is that if the fractional conversion is less than 1 but also greater or equal to 0, then it is reversible by equilibrium, meaning that it hasn't gone to completion. Is that right, Michael?
Sorry, what?
My fractional conversion, if it hasn't gone to 1, then it can still be reversible because it hasn't completely processed and stuff.
Yes, I wouldn't think about it as difference between reversible and irreversible. I would think of it more along the lines that you can still continue to react A.
Yeah, exactly. So you can continue to react it. Michael,
You realize they didn't hear anything I said, right?
They might have, I don't know. Let's keep going. Anyways, extent of reaction will tend to reach the equilibrium extent of reaction as opposed to maximum equilibrium. Maximum extent of reaction, which basically means that this will be lower than the maximum hypothetical extent of reaction, meaning that it could still be reversible or it could still keep on going throughout. Here's another general definition. So sometimes we like to normalize by volume. The reason we like to normalize by volume is so that we can have a volumaic rate, and the reason we like to have a volumaic rate is so that we can start dealing with concentrations and volumes within our equations, because a lot of times you'll be presented with concentrations as opposed to just normal moles. So if concentrations are used, you can just assume that, and keep in mind that sorry, this pen is really bad, is equal to C times V, concentration times volume. So what we're doing over here, we're taking our N and substituting it for C times V, and yeah, we're normalizing by volume over here. We're dividing by volume, and we have our stoichiometric coefficient. Now what this R stands for is basically the rate of the extent of reaction over time, how extent of reaction changes by time. And this actually makes sense. The reason this makes sense is that as you progress with the reaction, you're progressing through time, and once you progress through time, your reaction's also progressing, therefore your extent of reaction is changing. Pretty cool stuff. So we take this differential if you want to. You typically don't in most problems, and this is what you get. For constant reactor volume, this is the equation you're going to be using. A lot of times this is the only equation you tend to use, and this is your rate at a constant volume when your volume doesn't change but you have a changing concentration. Thank you, and that completes our introduction part of reactions. Michael is going to take the lead in the next video. Any wise words to say, Michael, or words of advice for these chemical engineers?
Leave.
Leave, yes. I wish I left. Bye.